Can you hear me? Yeah, great. So hello everyone, welcome to the session of debugging. I'm the session chair. My name is Zhang. I'm a lecturer at King's College London. It's my great pleasure to chair this session. And previously the chair was Andrew Steller, but everyone knows that he got COVID. So so today we have 7 talks, and I think the first 4 talks are 15 minutes, 10 minutes talk, 5 minutes question, and the last 2 talks are 7 minutes, 5 minutes talk, and 2 minutes question. So the first talk will be from Austin Mordahl from University of Texas at Dallas. So the topic is extensive framework for testing and debugging configurable static analysis. Let's welcome Austin.
Can everyone hear me? Okay. Hi everyone, I'm Austin. I am a PhD candidate at the University of Texas at Dallas, and I'm here to talk about some work that I did regarding the automatic testing and debugging of configurable static analysis tools. I did this work with my collaborators Zenong Zhang, Dakota, who's right there, and my supervisor, Dr. Shiyi. So I spent the last 5 years of my life researching static analysis, and the question is why? Well, it's quite a powerful tool that can model the executions of programs without actually running them. So this means that for domains like bug finding, where we primarily rely on dynamic approaches like testing, static analysis can serve as a powerful complement to those approaches. However, there's no one-size-fits-all analysis. Any analysis designer needs to carefully balance the competing needs for precision, which is the false positive rate, and soundness, which is the true positive rate. The optimal trade-off between these depends both on the use case of the analysis, as well as the input program itself. So in practice, how this is achieved is that most static analysis tools are configurable. This delegates the need to tune the tool to the end user. And as an example, I have an excerpt of the configuration space from Flowdroid, which is a static analysis that aims to find privacy leaks in Android applications. As an illustrative example, I'm going to focus on code elimination for this presentation. And as we can see from this picture, the command line help doesn't really give us that much information. It just says, use specified code elimination algorithm, and it gives us 3 options: none, propagate constant, and remove code. So let's go into the source code to actually see what this does. I have here some of the code from the implementation of the remove code setting of this option. And if we look at the documentation, it says, given a method, if it returns nothing, is side effect free, and does not call a sync, we can remove it altogether. So this is a transformation that aims to increase the precision of the analysis by removing code that is not relevant to the task of taint analysis. However, that's not actually what's implemented here. If you look at line 287, we have remove set to the conjunction of whether the return type is void, which is the left-hand side here, and does not have side effects and does not read this. Good so far. But then on 288, you see the or equals operator, and it's disjunction with does not have side effects and does not call sync. So in practice, we can actually remove code that meets either the conditions on line 287 or 288, but not both. This is a bug in the implementation of Flowdroid. And this bug demonstrates some of the difficulties in debugging and testing configurable static analysis. Namely, bugs may only occur under certain configurations. They might only occur under some input programs, like this one will only occur if you have an input program that meets some of the criteria but not all. And debugging this bug requires understanding both the analysis code and the code of the input program. There's a fourth issue, which is the oracle problem, which is if I run a static analysis on some program, how do I know if its results are correct? How do I know if it missed potential flows? If we're talking about Flowdroid, how do I know if what it gives me is actually correct? After all, the reason we use static analysis is to determine these properties about programs that are very difficult and tedious to determine manually. The naive approach for testing a configurable analysis would just be to have a separate test for each configuration. But as anybody who's worked in CIT knows, this is infeasible. I have some math up here showing how if we did the naive approach with FlowJoy, we would need 4.2 times 10 to the 13 different test cases for its test suite. However, the key insight of this work, or one of the key insights of this work, is that we don't have to take that naive approach. Instead, we can exploit the relationships between the settings of different options. So I'll illustrate this with an example. Let's assume that we're running an analysis on the same program under two configurations, which are indicated by these colored dots. The green dot is code elimination set to remove code, and the orange dot has code elimination set to none. All the other settings are the same between the two configurations. So if you recall from the documentation, this is meant to be a precision-enhancing transformation. So we formalize that using a partial order. We say that code elimination remove code proceeds with regard to precision code elimination dot none. In plain English, it is at least as precise. Also remember that this is meant to be a sound transformation. So we add an implicit constraint as well, saying that code elimination dot remove code should be the same level of soundness as code elimination dot none. And what this means is that we expect that remove code may remove some false positives from the results, but it should not affect the true positives that are emitted by the analysis at all. So we run both of these configurations, and because of the bug that I already showed, we actually get a weird result, which is that remove code misses a true positive that none finds. And this is a violation of the behavior that we expected that's encoded by our partial order, specifically this implicit partial order here that says that the true positive should be the same. However, how do we know which are the true positives and false positives? This is the Oracle problem again. So the second key insight of this work is that these implicit partial order relations that are induced by explicit partial order relations can be, well, the combination of both of them can be used to find bugs even without knowing the ground truths. So this table shows how we do that, and specifically I want to draw your attention to this cell. So the first row of this table shows the partial order relationships between a configuration C1 and C2. In this case, this is the same relation from the last slide, where we have one more precise than two, and both are the same level of soundness. The first column here shows the set relation between the results. So this means that C1 produces some result that C2 doesn't, although we don't know whether it's a true positive or a false positive. However, because we have all these partial orders defined, we can say that if it's a true positive, then we violated this partial order, that C2 should be at least as sound as C1. If it's a false positive, then we violated this partial order that says C1 should be at least as precise as C2. So even without knowing the actual classification of the results of the analysis, we can say that we found a bug, even though we don't know whether it's a precision or soundness bug. We've taken this insight and integrated, or not integrated, but developed a tool called ECSTATIC that leverages these relations to automatically test and debug configurable static analysis tools, with or without ground truths. The inputs to ECSTATIC are a partial order specification for an analysis tool, a set of input programs, and a configuration grammar. For time, I'm not going to discuss the role of the grammar, but I'd be happy to discuss that offline. And given these inputs, ECSTATIC first performs partial order aware testing. This means that for each partial order in the specification, ECSTATIC will generate a configuration and then mutate it so that we have two configurations that are different by only one setting, like the green and the orange configuration in the last slide, or 2 slides ago. It will then run this pair of configurations on each input program and compare the results to, against the table that I showed on the last slide to see if we find any violations of the partial order relationships. Once the ECSTATIC finds violations, it then performs violation-aware delta debugging to reduce the input program to just the failure-inducing features. This helps deal with that third issue that I pointed out with debugging static analysis, which is that a developer needs to understand 2 code bases. The reason that this delta debugging is violation-aware is that the predicate for the delta debugger is whether the violation still exists after it makes a change. And we have proposed, or not proposed, but we've created and implemented a 2-stage delta debugging approach that is specifically tailored for the task of debugging static analysis inputs. Again, I'm running a little over time, so I will be happy to discuss that offline, but let me go forward. When we designed ECSTATIC and implemented it, we had two main goals. First, we wanted to make sure that its results were reproducible. And to achieve that, ECSTATIC runs all of its analyses within Docker containers. We have a front end that the user deals with that takes care of all of that, so all of that logic is abstracted away. The second design goal was to make it easily extensible. And to achieve that, we defined clear extension interfaces for new tools and new input program sets. Yeah, so we've so far implemented 4 tools into ECSTATIC, Flowdroid, as I discussed before, and 3 Java data flow analysis tools, Sutwala and Dupe. As you can see by the bottom row of this table, the total lines of code needed to integrate those tools was at most 156. So if I may say so myself, it's quite easy to integrate new tools into ECSTATIC. We evaluated ECSTATIC's ability to find bugs, and in total, we found 74 bugs in these 4 popular maintained static analysis tools. As you can see, most of them were in Flowdroid, but we found bugs in all 4 of them. Oh, sorry. We reported about half of these, 42, to developers, and in every case where they replied, they've acknowledged that what we found was a bug. We so far fixed 3 bugs in Flowdroid and are working with the developers of Walla to fix more. For the Delta debugger, our 2-stage Delta debugger was able to achieve significant improvements over the baseline, which is hierarchical Delta debugging. Our Delta debugger was able to reduce programs, real-world programs, by 50% on average, compared to 6% with the baseline approach. At most, we were able to reduce a program by 99%, from about 65,000 lines of code to about 30. So in conclusion, ECSTATIC enables the automatic testing and debugging of configurable static analysis with or without ground truths. It provides an extensible framework for adding new tools and benchmarks. And so far, it's found 74 bugs in real static analysis tools. Thank you all so much, and I'd be happy to take questions now.
So by doing the partial load-over testing, how much testing effort reduction?
Testing effort reduction compared to what?
Compared to your entire health or exhausted?
So your question is the reduction of the testing effort. So in terms of actual machine hours, it's quite extensive. It takes tens of thousands of machine hours to do these tests, but we parallelize it. But it's all automated. So you can just tell ECSTATIC that I want to run tests on soot with this input program set, and as long as it has that configuration space, it can do it automatically. So in terms of effort for the developer, it's pretty simple.
Thank you.
Any other questions?
Thanks a lot for the interesting work. So one question is regarding the input with the partial order. So how complex it is? So the lines of code that you mentioned for supporting a tool includes that partial order specification effort, let's say?
I guess I can't go back. So as of now, to get the partial order specification, we have to do that ourselves, which means that we as static analysis domain experts have to look at all these configuration options and say, okay, that is a precision preserving transformation, that is a soundness preserving transformation, and we have to do that ourselves. So I have the table up right now, and at most Flowdroid had 77 partial orders, which we had to manually determine. We really hope that as a result of this work, we can motivate static analysis tool developers to make these configuration spaces explicit, not only to help testing, but also just as good documentation so that the user knows exactly what the analysis designer intended with each configuration option.
Yes. Yeah, thank you.
Does that answer your question?
Yeah,
okay.
Thank you.
Okay, thank you so much. Can you hear me? Yes, so as you can see, I'm not the first author of this paper. The first author, unfortunately, couldn't be here due to visa issues, so I will try to cover as best as I can. And this talk, we are going to continue the theme of removing statements, reducing developer efforts, and this talk is about software regressions. Regressions are unintended behaviors or faults that happen when you transition from a previous original version of the program to a new version of the program. And according to some studies, regressions, around 3/4 of upgrades results in regression failures, which developers take a lot of time to troubleshoot and fix. And there are techniques to help developers to troubleshoot and fix regression failures. I will mostly be talking about slicing-based techniques, and slicing-based techniques try to identify a sequence of statements that are directly responsible for regression. And they were shown in the literature to actually be aligned with the mind models that developers use to troubleshoot failures. That's why they are popular. Additional techniques that are also available in this context are spectrum-based techniques that try to pinpoint statements responsible for regression, and also delta debugging that try to pinpoint responsible changes. So we are talking about slicing, and I'm sure you're all familiar with slicing. Slicing is a technique. In this case, I'm talking about classical backward slicing. It's techniques that tracks dependencies backwards, controlling data dependency from the point of failure. And what I show on this slide are two separate slices for the old version of the program and the new version of the program. And as you can see, the slice for the new version of the program on the right doesn't even include the change. And that is because due to the change, the statement in line 4 is not executed, and as a result, the value of C in line 5 depends on the value of B in line 2 in the new version, versus in the previous version, it depended on value of B in line 4. And that makes B to be calculated differently, and that causes the regression in this case. But classic slicing cannot capture it intuitively. So to deal with that, there is an approach that was proposed in ICSE 2010, which is called dual slicing. And dual slicing is a dynamic slicing-based approach that tries to synchronize two slices to make it easier for the developer to reason about these failures. So how dual slicing works? It first aligns execution statement in both traces, and two statements are called aligned if they correspond to the same code statement and also executed under the same control path. And further, so you can see in this example, all statements besides the one in line 4 are aligned, and the one in line 4 is only executed in the old version, but not in the new version. Now, aligned statements can further be divided into identical, which means that they operate over the same data, or otherwise they call data divergence. So statements in line 5, 6, and 7 are data divergence. Now, once we do that, dual slicing has two ideas. First, they remove all statements that are identical. All aligned identical statements, being identical, probably not contribute to the failure, so that can be removed. And the other thing that dual slicing does, it tries to synchronize slices by moving aligned statements that happen to execute in one version of the program but not in the other, moving them to the other version together with their transitive dependencies to give developer a more comprehensive, symmetric picture about the failure. And the author of this paper show that dual slicing produces more precise and more concise slices that can help developer to pinpoint failures, including omission errors, like in our example on the right. Now, we were intrigued with this result, and the overall study is how to help developers to integrate slicing approaches into debugging, or to understand why they are not used, or to understand how to make them use. So in this big scheme of things that we are trying to do, we performed a study in which we applied dual slicing on a set of realistic regression failures, and we took 250 regression pairs from the famous defects for J repository. But these defects for J failures are kind of simplistic and very, focused on a particular failure, so we further extended it with a set of 8 big, real client library regression failures, where the upgrade in the library causes the client to fail. So we run dual slicing on all these benchmarks, and what we observed that, yes, it works really well. It reduces the focus of developer from the trace to slice significantly. But then we saw that slices are still extremely, extremely long, more than 1,500 statements on average, which is still a lot to be able to comfortably develop. And moreover, what we also observed that not all statements in the produced slice are actually really relevant for the failure. And let me tell you what I mean by this. So what I mean by this, that's kind of going one step backwards. We already figured out that dual slice will contain 2 types of statements, aligned and unaligned. But when we analyzed the slices, we observed that there is a different orthogonal separation. It also contains statements that are common, so unchanged between the versions, and statements that changed between the versions. And the number of common statements is actually significantly bigger than the number of changed statements, because changes in programs are relatively small compared to the entire code base. So there is large chunks of common code which is not likely responsible for the failure directly. But we also thought we cannot just remove this code, because if we remove it, we lose the entire flow of information inside the slides. So that gave an idea to the approach that we introduced in this paper, which is called INPRESS, and it stands for Information Preserving Slice Summarization. And the main idea of this approach is actually to summarize, not remove, summarize big chunks of common code while keeping dependency between the relevant statements. Now, the rest is very simple to explain. It involves some relatively complicated machinery based on analysis of traces and slices to execute, but it's super simple. So what INPRESS does, it first identifies blocks, aligned and unaligned blocks, trying to synchronize between the slices. And once it identified all the blocks, it summarized each block in terms of input-output variable dependencies, where output of the block are all variables that will be used later in the slice, and input to the block are all variables that these outputs are depend on. And once we did that, we saw that we can still produce accurate slices which are even shorter, significantly shorter than dual slices, 76% reduction with 207 statements on average, which we think is more manageable for developers to inspect. So a quick summary so far. So far I told you about the main contribution of this paper. One contribution is a benchmark of real big regression failures with real client library pairs. Then our study of applicability of dual slicing for identifying regression failures, and our conclusion that slices are still very, very large and not all statements are equivalently interesting. And our approach for further reducing the size of the slides to help reduce developer effort when troubleshooting failures. Now, in 1 minute, I want to add where are we going with all that. So from the beginning, our overall goal was to see how to facilitate integration of slicing-based techniques or programming analysis-based technique into the debugging workflow. So we kind of envision a workflow where a developer can say, let's inspect a failure, press a button, and all irrelevant statements that deemed by our approach irrelevant will be grayed out or otherwise marked in the debugger. And then developer can inspect the dependencies, will say, okay, value of D, what it depends on, and they will be given the information that the value of B actually depends on line 2 in the right-hand side and line 4 on the left-hand side, and why this happens. And that's how we hope we can make developers more productive, and we are performing in our current work and more extensive study of how helpful this is. So that's all for me for today. I will leave the slide with the summary here to save time, and I'm happy to take any questions. Thank you.
Thank you for your nice presentation. So I have a question, like what I understand from the presentation is that you were trying to identify the code differences from different runs. So you are trying to remove the statements which are common in multiple runs, and you're only identifying what are the different executions in different runs.
Is that the question?
No.
Oh, okay.
What I understand. So my question is, if I'm correct, so then how different this approach is from the spectrum-based fault localization?
Right. So I think that's a very key question. So thank you for this question. It's very important. So first thing, we are not trying to remove. And that's what I was trying to emphasize, but I'm happy to emphasize this again. Removing, we don't believe it's good. Spectrum is removing. And there are many studies that show that developers lose context. So we are not trying to remove. We are trying to collapse and summarize the dependencies. We don't just let these blocks out. We keep a dependency, as I was showing in the previous slide, to indicate that there is code, and there are dependencies between variables in preceding code and the following code. So our key idea is exactly not to remove.
Yes, but I have another question, like, are you targeting any specific problem to solve these things, or in general, developer can use this tool to make their debugging process easier, like, or are you targeting any of the specific things, like, say, flakiness removal or debugging the flakiness things? Like, do you have any specific things, or in general, it will be helpful in debugging?
Right. So at this point, we don't target any specific kind of problems like concurrency or flakiness. No. We are trying to understand and investigate. Slicing is with us for 30 years at least. If you read papers on slicing, they say slicing is great and it helps developers, right? Everybody says that. And yet, if you look at commercial tools, commercial IDs, none of them is using slicing.
Yeah.
So our intention behind this work is to figure out why. If it's such a great tool, why developers don't use it? And our intuition is that they are not used it because slices are still super long.
Yes.
So basically it doesn't help them much. Now, going to spectrum also doesn't help them much, not ours, but other studies shows that when they don't have context and they have individual statements, it's not helpful. So our basic premises is to try to reduce the size of the slice and integrate this into tools and actually go to the next version of debugging for any kind of problems.
Okay, thank you.
I have a question. Thank you very much for the very interesting work. So so you mentioned that Defects for Java is simple. So you have the open source, the client library framework. So could you explain more on the key differences on the two data sets? I mean, in terms of your results.
Right. So let me clarify this. So Defects for J is based on realistic cases as well. It's not a made-up cases. But what we observed when we look at these cases, all changes that happen in each benchmark of defects for J are directly responsible for a failure. So it doesn't have changes that just happen and not lead to the failure. So it's distilled to contain only the minimal set of changes that are responsible for the failure. And we also observed that a lot of changes appear towards the end of the trace. So it kind of skews the overview of the trace, of this slice of the trace, and how changes are distributed across the trace, and how many of them are relevant for the failure or not. Versus in our additional benchmark, it's in the wild. There is a lot of changes. Not all of them are responsible for the failure, and they are distributed very widely.
Thank you. Any other questions? So if not, let's thank Julia
Thank you very much.
For the presentation.
So thank you very much. It's a joint work with Jan Reichl, Volker Gruhn, and me, Stefan Hanenberg. And yes, it's about, does the Stream API benefit from special debugging facilities? And let's directly start with the results. So what did we do? We performed a randomized control trial on the stepwise debugger in comparison to the Stream debugger, and it was performed on 20 professional Java developers. And what they had to do is they were given some piece of code where a filter was incorrect, and they had to identify the incorrect filter and have to fix it. And they either used the stepwise debugger, so the traditional debugger, or the stream debugger. And our measurement was the solution time. So each developer did the task until the correct solution was delivered. So what was the main result? The first result was the stream debugger has, in general, a strong and large effect. And so what does large here mean? On average, the stream debugger or the stepwise debugger takes about 100% more time than the stream debugger. But there's a special situation. The special situation is if the failing object is known upfront, the loop debugger requires less debugging time. So the stepwise debugging is not under all circumstances worse than the stream debugger. So let's just, what is the overall interpretation? Well, stream debuggers seem to be appropriate or good in general for debugging filters, except in situations where the failing objects are known upfront. And let's just take a look what we currently speak about. So this is an example of filter operation on using loops. So we have a for loop, and this loop iterates a collection, and then we apply 3 different filters on that. And we did it here with 3 different if constructs. We also could have used AND operations between them. That's not important. Important is that we have 3 different kinds of operations applied on a collection element in order to make sure that it gets into the result. And if we have the stream API, it looks slightly different. Again, we have filters, but the filters now are defined in terms of lambda expressions, and they are given to the filter operation. And then we have some additional code for collecting the elements. So what do we already know about the comparison of loops and streams? Well, we had last year at ICSE we had a presentation where we showed a readability study on loops and streams. And so developers were asked what is the result of a query, and some code snippets were given and so on. And it turned out that the stream API had a positive effect on the response times with quite high effects. So what is the open question? The open question from our perspective is we know something now about readability. It's a good thing that readability is improved by the stream API, but we mustn't forget that other things happen while developing. And one thing that happens is, well, we debug code. So it's not only that we read code and play with it, but we execute it, we have debuggers. And here we have 2 different kinds of debuggers that are currently on stage. It's the traditional stepwise debugger that we always find in IDEs, but we also have a stream debugger as implemented in IntelliJ. And the general question is, does the stream debugger have an effect on the debugger? So just to give you an idea what both tools look like. So this is the stepwise debugger that all of us know. So it's again here an example consisting of a collection of 6 integers, and we're just filtering all those integers that can be divided by 3 and which are squared numbers. And in a stepwise debugger, we typically have breakpoints somewhere, and then we go step by step through the code. In a stream debugger, it looks slightly different. So there, we have here the same example, and we see the visualization is really different. So instead of having this more code-focused representation of where we currently are and what the lines of code do, we have here a visualization of the different filters and the incoming collection and the outgoing collection. So we see what elements from the left go to the right, and we can click through the different filters in order to check out which elements are or exist throughout this chain of filters. So what are the key differences? Obviously, stepwise debugging means we step through each filter, typically per object and typically line by line. And in a stream debugger, it works completely different. So we're selecting filters and we typically compare result sets. So it means that from a cognitive perspective, quite different things are going on for the developer. What do we think possibly influences the debugging speed? So in case there are differences in debugging speed, well, probably the number of filters matter and probably the number of objects matter. So just as a trivial example, let's assume there's just one single object. We don't assume that the stepwise debugger is better than the or is worse than the stream debugger. In the same way, if we have a small number of filters, we also think the situation is comparable, but we also think that we have to take care what the position of the failing object in the collision in the collection is. So if failing objects appear very early, stepwise debugging probably is easy. If it appears late, we probably have more effort in using the debugger. The position of the failing field also probably plays a role. And the last point, which is probably, and it finally turns out that it was one of the dominating things, is whether or not we know the problematic objects upfront before we do the debugging steps. So how did we design the experiment? Well, we designed it with a subject experiment, and we had relatively simple filter criteria. So we just had fields and fields compared to literals with corresponding operators such as larger or smaller, etc. And our complete experiment is just generated tasks. So we generated all the tasks from repositories, so we didn't have any hand-selected tasks here. And in case you're interested why, I'd be happy to answer a bunch of questions on that. Again, we used 20 professional developers. They were already familiar with streams in industrial context, so we didn't really have to train them. What was the experimental layout? We had the solution time as the dependent variable, the 4 independent variables that I already described. So first of all, the debugger itself, the failing object position, where the field position was, which means where the filter actually appeared, and whether or not the failing object was known upfront. And the fixed variables in the experiment was the number of filters, and the number of objects were always 30, and the number of objects in the collection were always 40 objects. So developers were given a piece of code, bunch of filters, and they had to correct the incorrect filter. So what were the main results? They are not that interesting. So it just means all of our variables were significant, and the debugger, as already said, plays a larger role. On average, the stepwise debugger required approximately 100% more time. But the interesting things are the interaction effects. The interaction effects here, it turned out that in case the failing object is known upfront. So if I know which objects are responsible for a failing filter, suddenly the stepwise debugger was faster in our case. So although in case the object is not known, the stepwise debugger is terribly slower, about 190% slower. In case the object is known, the stream debugger is suddenly slow. The other interaction effect is on the object position, so the position of the object in the collection. If it appears relatively early in the collection, we didn't measure any significant difference at all. But in case it appeared very late, the stepwise debugger was about 200% slower than the stream debugger. So what did we conclude from the study? Well, stream debuggers seem to be more efficient than stepwise debuggers in case the failing objects are not known, and in case the failing objects appear relatively late in the in the collection. And as I said, what's interesting is that we generated all the tasks. There are a bunch of threat stability that could be discussed here, but we don't have the time for that. And well, what we also conclude is we speak a lot about debugging and how people should debug and what tools they're using, but in fact, we don't have that much empirical knowledge about interaction patterns between developers and the debuggers, and I think many more experiments are necessary for that. And in case you're interested in the experiment itself, you can download everything from this link. So you can download the experimental material as well as the data. So thank you very much. I'm slightly 1 minute over. I hope that's okay. And in case there are questions, I'd be happy to answer them.
Thanks for the talk. I think, yeah. We have time for 2 quick questions.
Hi, yeah, thanks for the great and interesting talk. I was just wondering if you have like some idea of why the stepwise debugger is like so much better than the stream debugger in like the case of the non-failing object.
So I think, well, when you know the object, so in case you already have the object in mind that is responsible for a certain problem, it's relatively trivial for you to write additional code with an if statement to get exactly to the point where the problem appears, or you have a conditional breakpoint or whatsoever. So I think in that case, it's trivial to identify it, but it's no longer that trivial to identify the same object in a long list in a collection.
Okay, thank you.
Does it answer the question?
Yeah.
Other questions? So I have a quick question. So when you do the user study with the developers, how did you select the developers? How do you control the randomness in you know, for example, in the different experiences among those developers?
Okay, could you just repeat the question once more?
Sorry. I mean, you choose 20. Can you hear me now? Can you hear me?
Yeah, yes, now I can hear you.
Yeah. So your study chose 20 developers, right, for the study? So how did you select developers? How do you get, for example, guarantee that their experiences are the same and don't affect your results?
Well, the thing is more the opposite. So before we run experiments, we run a huge bunch of N of 1 trials where we get an idea of the effect sizes. And at the end, we were relatively sure what the result of the experiment will be. And so it was enough for us if someone just was able to articulate to us that he already used the streaming API and he already used or has seen the stream debugger. And from our perspective, it was already sufficient. And actually it turned out that it was sufficient because in the end, they were faster with the new tool.
Thank you very
Does
much.
it answer the question?
Yeah. Thank you very much. Okay, so let's thank Stefan again for the talk. Thank you.
Hi everyone, my name is Kabin and I'm a PhD student from KAIST. Today I'll be presenting our paper titled Fonte, Finding Bug-Inducing Commits from Failures. This work was done with Nanyang and Shin from KAIST and also Jinggon from SAP Labs Korea. In a modern software development process, developers continuously make code changes or commits to the software, and sometimes the commits can contain a bug. And those specific commits that introduce the bug into the software system are called bug-inducing commits, or BIC for short. When it comes to debugging, especially large software, finding the BICs can be a huge time saver. It can facilitate the bug assignment process, as BIC will let us know who introduced the bug, and it may also speed up the bug fixing process by helping debug assignee understand the root cause. However, finding the BIC isn't always an easy and trivial task because sometimes bugs can lay dormant for a while before they're found. For example, code changes are often bundled together and tested at the same time to save on testing cost, which is also called batch testing. Therefore, if test failures happen in this phase, it is not straightforward to know which commit is causing the failure. There are also many cases the bugs are even reported by users or QA engineers after the release. So to identify BIC, people have come up with various techniques. The first one is the famous bisection method that performs a binary search on the commit history using bug revealing inputs or test cases. Consequently, this usually incurs additional program execution or analysis cost. The second one is the SEZ-like algorithm that uses the bug fixing commit to trace back to the BIC. Therefore, this cannot be done during the debugging because there is no bug fixing commit yet. The third one involves IR-based techniques such as locus or FEL-BERT that find the BIC by analyzing the lexical or semantical similarities between a given bug report and the commits. As they often rely on the human written contents in the bug report, if such contents are not available, this becomes less effective or even not applicable. The last one is the coverage-based technique that filters out that narrow down the BIC search space using the coverage of the failing task. So this is actually our previous work, so let me explain more about this work in the next slide. In our earlier work, we had a simple assumption that a commit can be a potential BIC only if it either introduced or modified code elements that are executed by the failure. So using this assumption, we can simply narrow down the BIC search space like this. First, we measure the coverage of the current failing test cases, and then track down the commit history of the covered elements. Finally, we keep only those related commits as BIC candidates. When we evaluated this with using defect version 2, the results show that failure coverage can reduce the BIC search space by around 88% on average. Although this is a significant reduction, we still have a remaining question. What is the actual BIC among these candidates? So to solve this question, we propose Fonte that can rank the BIC candidates according to their suspiciousness. Fonte consists of 3 stages, where the first stage is identical to our previous work that filters out the failure-relevant commits using coverage. In the following stage, it further detects and discards the style change commits that do not affect the program semantics. And in the final stage, the BIC candidates are scored. To score the BIC candidates, we started with this necessary condition of BIC from our previous work. Using this condition, we were able to reduce the BIC search space, but cannot pinpoint the BIC. So we developed this idea to the assumption that a commit is more likely to be a BIC if we introduce or modify code element that is more relevant to the failing task. And here we know that the relevance of code elements to a given failure can be measured by the existing fault localization techniques. So based on that, we can again translate this one to a new assumption like this. So to realize this assumption, Fonte basically transforms the code level suspiciousness scores to the commit level using the commit history of each code element. More specifically, Fonte uses a voting scheme where each code element votes for its relevant commits. Here we have 2 voting rules. First, the more suspicious element has a higher voting power. In this equation, the denominator is the alpha ranking of the code element, where tau simply decides the type ranking scheme during the ranking, and alpha controls whether to use the original alpha score as a numerator or not. But regardless of these hyperparameter settings, this equation always gives the higher voting power to more suspicious elements, like this. And the second rule is called depth-based decay, which penalizes the older commits. So suppose that we have a code element with voting power of 1, then among its relevant commits, only the most recent one gets the full vote, and the voting power exponentially decreases for the older commits. And here, the larger the lambda is, the greater the decay is. And this figure summarizes the whole voting process. After all suspicious code elements vote for their relevant commits, the score of a commit is defined as the sum of the votes it received from the code elements. Here we ask our first research question: How accurately does Fonte rank the BIC? As an evaluation data set, we used 130 ground truth BICs for defect-free faults. When implementing Fonte, we used git log to retrieve the commit history and OCI as a full localization score. And as an evaluation metric, we used accuracy at n and mean reciprocal rank. We first compare our voting-based our FA ranking-based voting scheme with other two baseline voting methods. Here, score means the voting power of a code element is simply defined as its FA score, and the equal voting gives the same voting power to all code elements. And the results in MRR show that our ranking-based voting schemes outperforms the two baseline voting methods regardless of the hyperparameter settings. And you can also see that the depth-based decay increases the ranking performance, especially when lambda is set to 0.1. So in sum, Fonte has been shown to be the most effective with these hyperparameter settings. And this line graph on the right side shows the ranking performance of Fonte in terms of accuracy at n. And you can see that Fonte can rank the actual BIC within the top 10 for 85% of the studied bugs. If we compare this with state-of-the-art IR-based techniques, bug-to-commit and FBI-BERT, you can see that Fonte significantly outperforms their performance. And even when they are applied to the same reduced search space with Fonte, you can see that Fonte still shows a higher ranking performance than the baselines, achieving at least 40% higher MRR. So based on this good ranking or scoring performance of Fonte, we also propose weighted bisection algorithm that combines bisection with Fonte to guide the BIC search more efficiently. So during the weighted bisection, a search pivot is set to the commit that can help the amount of Fonte-generated scores instead of the number of commits to check the point of greatest ambiguity where the chances of having BIC in two directions are almost equal. So this example illustrates how weighted bisection operates. So our second research question asks, how efficient is this weighted bisection as compared to the standard one? And the results show that weighted bisection requires significantly less iterations than the standard bisection, leveraging the Fonte-generated scores. And even when the standard bisection is applied to the same reduced search space with Fonte, you can see that Fonte's weighted bisection still requires less iteration than the standard bisection plus. Finally, we also applied Fonte to the actual batch testing failure data from SAP HANA, and you can see that it was able to rank the actual BIC within the top 5 for 87% of the study bugs, where each batch contains 19 commits on average. And you can also see that weighted bisection can reduce the weight bisection iteration by 33% on average. And as one bisection iteration in SAP HANA sometimes takes a few hours, we expect that this can bring huge time saving. So in this work, to find BIC while debugging, we propose Funte that uses the FLS scores to rank the BIC candidates. We show that Funte significantly outperforms its baselines, and its score can also accelerate the bisection process as well. Finally, we applied Funte to the batch testing scenario of SAP HANA and confirmed its effectiveness in industry setting as well. There is actually one more research question in the paper, so if you're interested, please refer to our preprint. So that's it for today's presentation, and thank you for your attention.
Questions?
Yeah, thank you for the presentation. I'm wondering, why would you care more about the bug-inducing commit than the bug-inducing line of code in debugging?
Bug-inducing line of code. Like, as I first said, by finding the bug-inducing commit, you can know that who introduced the bug. So it can, aid the bug assignment process, and then bug-inducing commit also help you understand why this failure happens by, by showing the possible buggy lines in the code. So, and also by finding BIC, you can increase the full localization performance as shown in earlier work. So maybe they can collaborate as well.
Okay, probably. But if you can get the line of code, then you can also do like git blame to see which commit that comes from.
Yeah, okay. But, it is not always that the most recent commit is the BIC. So that's why we cannot simply use git blame, to find the BIC.
Okay, thank you.
Yeah.
Oops.
Thank you for the talk. My quick question is, I think you have evaluated on the data Dfa4j and HANA, right?
Yes.
So have you evaluated on a very complicated BICs? I think because there are many commits that are a large bunch of changes, but we know that this is a BIC, but it can be mixed with very many other changes.
Yeah.
Have you evaluated on the very complicated commits of this coverage-based approach? Thank you.
We haven't analyzed the specific commit, but in those cases, I think that by taking the intersection between the failure coverage and the BIC will help you narrow down or prune the other unrelated code changes. I think does that yeah.
So thanks for your talk. My name's Shane McIntosh from the University of Waterloo. I'm curious about the industrial application.
Yeah.
Because I have an industrial partner who has a similar problem, and they tell me that the baseline I have to beat is their engineer's intuition. So they would run this build with a batch of 19 things, and the engineers would look at the failure log and say, I think it's that commit. So instead of trying to beat basic by section, do you think you can compete with non-artificial intelligence?
I'm not sure, but in the case of SAP HANA, they find a BIC using the standard bisection tool, so that's why we use this as a baseline. But yeah, we'll continue this work to that direction. Okay. Thanks for the question.
Okay, sorry, we don't have time for further questions. You can talk during coffee break. Let's thank the speaker again for the talk.
Good afternoon, everyone. My name is Wajdi. I'm presenting this paper on behalf of all the co-authors. So everyone know our software engineering, we have to do a testing in every software in order to have like a reliable software, a free bug, but there is a bad practices in software testing. It's called test smell, and some developers making these mistakes or dealing these bad practices on it. So in 2001, there is a catalog proposed by Van, which is showing that there is some type of test smell, and it's showing gradually improving through the years. So this is a given code. In order to test a given code, a student may writing multiple test cases, and in order to testing a piece of code. One of the student writing this list of test cases, which it doesn't contain any of the test smell, and the other student writing test cases which is contain assertion relate, and this assertion relate is can be someone making multiple assert under the same test cases. And the third type of the student, they might writing test cases, which is the test cases that are writing multiple methods under the same test cases, and these test cases are equivalent because all are producing the same type of the testing outcome. So, however, the student exist test smell, and some of them do not exist test smell in their test cases. So the question is that, is it okay to write test smell in the testing method? So previous studies argue different through this matter. So multiple researchers has a different opinion about it. The first study is exploring the smell, and these studies is saying that it's not okay to have test cases or test smell into the test code. And the other study is just, developing or discovering student perception and challenging when practicing unit test. So, and the third one is assessing the impact of the test cases in the checklist. So they seeing the student where the checklist, and they try to see if they cover it or not. So the last study here is evaluating the impact of the assertion relate smell on the student performance and behavior during the source code execution. And this study said that test smell does not impact the student performance, and it is actually a good code. So the question is here, our goal is to determine whether assertion relate and eager test negatively impacting the student troubleshooting and debugging. So to do that, we're comparing the effective of a smelly and not smelly test suits on the student debugging performance. So our study has one research question: to what extent do assertion relate and eager test impacting the spend time with the student in the debugging failing test cases. So our study have been through multiple stages. The first stage is that creating a project. So in order to create the project, we created calculator program. So the reason of that, because we want to having a simple and easy and every project that everyone can understand it. So a student do not overwhelming with the features of the program. So we did that in Java programming, and then we have 8 functions. All these functions is quite simple and everyone know it. And even the first year of the computer science, they know it, how is this work. So some of the functions like subtraction, multiplication, average, and etc. So then we created, after we did the project, we went to ECSTATIC to automatically generating test cases. And then we have 3 types of project. The first project do not have any test small, is all test cases. And then the second project has assertion related test small. And this list of the number of the test cases for each type of project is showing here. So the first non-smelly, we have 40 test cases. and the assertion roulette, we have 8 test cases. So in assertion roulette, we have 1 test cases that combine all the 5 test assertion in the type of the submission and subtraction, etc. So, and we have the suite 8, which E, which is eager test, which has 9 test cases. So then we evaluating our project, all these cases in order and TS detect in order to make sure that this type of project, the class A and class E, category A and category E, having test small. After that, error creation. So we used a bit test in order to creating bug or issues in the code. So actually is switching, for example, the symbol from subtraction or division into like sum or division. So it's like if there is subtraction, then it's changing to summation or something like that. So then we targeting the course. The course it shows that undergrad level student in software engineering. So the student have more 2 years and more experience in programming. We providing information about like how they debug and how they trying to finding issues, and then we give them a familiarity of how they can finding a bug and issues in the source code. So after that, we did a pilot study. The pilot study is on 4 undergraduate students. And the purpose of that to clarify the instruction for the student and also to provide the documentation. The documentation was into operating system, Windows and Mac in case if we have a different setup. And then we also try to make sure that the environment set up for the student before even they starting their experiment. So in order to not having more time while they struggle with the environment, and we need to the time to start when they're starting the experiment. So the participant, we did our experiment in 2 different semesters. The first semester is 65 participants, and the second semester is 65 participants. So in the procedure, we provide a video tutorial for them so they can watch it and they can see how is the setup. And then we provide also an instruction to set up, and we give them a presentation how is the experiment goes. So this is the statistics of the participants. We eliminating 25 students. The reason of that, some of them did not completing the experiment and the other did not fill the survey. So we eliminating these students because they did not completing the experiment. So we end up with 96 students, and this is the statistics of each category. In the procedure, we're splitting the student based on rows. So in order to eliminating the bias in the data, so we did not consider who has more experience in programming and the other experience in programming. We just split them based on the category in order to now anyone has get any help from the others. So in the data collection, we collecting the source code that after they fixing all the bugs, and then we wanted to calculating the time, the fixing time, and then we have the survey where we have 3 questions, 2 multiplications, and 1 of the open question. So study result, in the experiment result, we can see that the precision of the test decimal and assertion roulette and eager test are highly impacting the time where the student taking longer to fixing the bug comparing to the non-test decimal. And that is showing that in our study, smelly tests are negatively impacting the student debugging and process. So also the previous study by Bia finding that is saying it's assertion roulette do not impacting the student performance and the testing, and it's actually assertion roulette is a good code. So our observation constructed the finding of Bia, whereas conjecture of the assertion roulette may no longer be considered as a code smell. So the situation result here, reviewing that multiple reducing methods and conjecturing switching between multiple code files, and also troubleshooting that, potentially increasing their conjecturing load and debugging time. So the result from the survey, we asked a question: were you able to fixing the errors detecting by the test cases? So we found that 13 of the students did not completing their where they were not able to locating and fixing the source code. And this is the distribution of the finding, whereas 3 students participated in non-similar test and 3 also in eager test. But we also found that 7 participants in assertion relay talk were not able to fixing the source code. So the testing cases. So participant assigned assertion relay test, so it has highest percentage where they're not able to completing the assignment in giving time frame, where we give them a time frame for 2 hours. So as you can see here from the bar chart, where is the non-smelly test code that's showing that more percentage of stronger agree when we ask them the process of finding the error and detecting by the test cases. So that's obviously because there is no test smell, and it was straightforward for fixing each test cases. But we can see from B and C, assertion relate and eager test, it has a different pattern, because and the student most likely they are agree and disagree, where it's simple and easy to finding that. But because the student did not notice any difference between the smelly and non-smelly test methods. So the takeaways, teaching students about designing and code small, writing quality test cases, code review should be also not limited to production code. So education that should emphasizing also on the reviewing code for test code. Producing tools to aid developers with the detecting, correcting test smell. So there is a limitation also in the tools that helping practitioner and researcher and student to detecting test smell, which is limited more on Java, and other programming is still not developed there yet. Exploring the type of test smell are unique to specific programming languages. As I mentioned, that there is a certain tools that more limited to the Java and not other programming language, and test smell are not unique to JUnit based on the test suite. So our threads and validity here, the participant, because our participant only limited for one school, one of the university, so we applied that for 2 semesters. In order to avoiding these bias, and also we selecting a simple project as a calculator, so they are familiar with the type of the project, and they do not overwhelming with the features and implementation for the project. So selecting of test smell, in order to select test smell, we selecting test smell based on the reviewing previous papers, research papers, and also we looked into the most popular and frequent smell, and we found that assertion relate and eager test is the most frequent and used test smell. So in order to summarize here, assertion relate is taking longer time for the student to fixing the bugs, and some of them they not even notice that there is a smell in the test cases, and also there is a limitation where is the tools that for developers to develop beside the Java. So here is the replicating package, all the source code and the videos and the tutorial and documentation is there. If someone want to bring that further for more different test smell, feel free to use that. And here's my contact information if anyone has any question. Thank you.
Probably I would ask quick question. So you have different findings with previous work. So what are the possible reasons, in your opinion?
Well, that's a good question. So the last study on the right, they did a similar study of ours. They are in the same scope, but in different distribution. What they did is that they let the student developing their own source code, and then they're writing their test cases. So a student, they could not find there is a negatively impact because they are implementing whatever they ask them to do. But what we did is that we give them the source code, we give them the code, we tell them that there is a bug and fix it in order to evaluating whatever to evaluating or to assist if there is negatively impact or not. And this is where we can find and determine if there is negative impact or not.
I see. Thank you very much.
Mm-hmm.
Okay, so I have to move to the next talk. Let's thank Raj again.
All right, thank you. So this is joint work with Luis, Miguel, and José. And the context is a debugger for JavaScript regular expressions. Now, the question is why we need that? Well, if you look at code with regular expressions, then it turns out that it's very complicated. So that regular expression over there is supposed to be, validating a URL. And it turns out that is invalid, that there is a problem. Actually, this is a Stack Overflow question that someone is saying, well, I'm trying to a regex to validate the URL, and I'm getting result as true, but it should get false because URL contains a comma. So just after dub, there is a comma instead of a dot. Now, the question as a debugger is you need to go and check the regular expression, right? And you need to fix the regular expression. So what we are showing here is a demo of our prototype that actually helps you in debugging such problems. Now, for those of you that are aware of debuggers for regular expressions, you may be asking yourself, so what's the problem with the current tools? Why are you coming up with yet another tool, right? So, well, it's true that there are many debugging tools for regular expressions. There are actually, 26, at least that's the one we know. But only 3 tools support code stepping of regular expressions. And those are the 3. If you go to the paper, you will see that we have analyzed the other debugging tools. But they come with limitations. So the limitations are, well, they typically are standalone regular expressions debugging. So it means that you need to copy-paste your regular expression from your code base to some other place, then you debug there, then you need to copy-paste back. And that's, well, it's not the ideal situation. There is also limited control over the matching process. You don't have, things like breakpoints and stuff like that. And also there is no global view over the matching process. And of course, I'm coming up with these limitations because those are the limitations that we will be addressing, right? And that's why. Maybe there are more, but anyways, we are only addressing this. So that's what RegStepper offers. So it's an integrated regular expression debugger. So the idea is that you don't need to copy-paste your regular expressions. You debug the regular expression in your code base. Then it also gives you this fine-grained control over the matching process. So you can put breakpoints. It's just like regular classic software debugging. You can just, set a breakpoint. You can then step-by-step your code and whatnot. By the way, these are screenshots of the tool. I will give you a link to the tool at the end if you want to play with it. And then we also have this global view of the matching process so that you have a sense of where you are in the regular expression, right? To put it simple, the architecture is as simple as these 3 steps. So, of course, we take as input the regular expression. Well, the code. From the code, we check where there are places with regular expressions. Then we have this rexref, that's where we actually compile the regular expression into this intermediate representation. That in our case is a JSON file or a set of JSON files. And those is our intermediate representation. So we are going to use those files in order to do the code stepping and the breakpoints and whatnot, right? So that's I was talking about this and I forgot to push the button. Now, in terms of evaluation, so we evaluated with the benchmark test 262. As you can imagine, parsing regular expressions is not a small feat. And so what we did was we also tested whether or not our prototype could parse all regular expressions out there. So there are a few that we cannot handle, but that's just a few. So out of the 729 regular expressions in this benchmark, we can compile and do the debugging in 718. So we get 98% coverage of all the regular expressions. There are still some work to do, but yet the numbers are pretty good. And then, well, this is about debugging. So what we did was we crawled Stack Overflow. That's on the right-hand side. So we called Stack Overflow. All these details are in the paper and also in the data in the online information. But anyways, the idea was we get all these Stack Overflow problems, and then we try to fix those problems using the prototype. And so we managed to find all those regular expressions in Stack Overflow and fix the problems, and we actually checked whether or not the problems were fixed with the authors of the questions. Okay. Yeah, and well, this is just a demo talk, so it's like 5 minutes, so I don't have much time. So I'm not going to do a demo here, but if you want to try this out, you can just go to that link over there. If you visit that link, you can just copy paste some JavaScript code with a regular expression, of course, and then you can just debug your regular expression. But anyways, as a summary, so I've just shown an integrated regular expression debugging kind of IDE kind of thing. At this point, it's not integrated with any IDE. We could, of course, do it, but it's not yet done. Then the prototype gives you fine-grained control over the matching process with breakpoints, so that gives you the feeling of a classical debugging experience. And also gives you this global view of the matching process with matching trees, which helps you understand where you are in the matching and where the problem happens. Once again, if you want to try it out, just check it out. And if you have feedback, of course, it's more than welcome. Questions?
One quick question.
I have a quick clarification.
Yeah.
Can you look at the tool screen? So that black dot is your breakpoint?
Yes,
okay.
Correct.
Can you put it anywhere in the string? Okay.
Yes. Yeah, you can just put it wherever you want. And then the thing is that, so let me go. So what you see regular expression is that then, you have two windows. One is where you put the regular expression, then it will have the compiled JavaScript. So some people like to see it, the compiled version. Then you have the output is just a regular expression. The code step, the dot is you put it wherever you want. So in that case, we have to write one at the beginning and one towards the end, just before /s.
Thank you very much.
Yeah.
Yeah, any other questions?
Thank you very much. Nice presentation. Actually, I have one question. Did you tackle the issue of readers actually for this one?
Say again?
Readers, like, so for example, if the regression has like backtracking problem, like how does this handle it actually? Or
yeah, so the tree representation helps you understand where the number of backtrackings and stuff like that. So we also give that information in that output tab. So you get information about backtrackings and stuff like that.
But if it has like infinite backtracking, like does it like crash or like does it?
Oh, it doesn't crash, but after a number of iterations, we will stop.
It's stop.
Yeah.
Okay.
So
Thank you.
It won't crash.
Okay. Thank you.
Oh, it's not supposed to crash, let me put it this way.
Okay, let's thank Ray again.
Thank you.
Hello, everyone. I'm Peng Kwang. I'm a PhD student from Lund University, Sweden. Today, I'm going to present you our paper towards Gates Assistant Developer Tools. It's a short positioning paper. This is a work done by me and my supervisors, Emma Söderberg, Diderek, the hoster, and Martin host. As you may know, many crucial software developer activities are Gates-driven. For example, code review and debugging. Code reading underpins all these activities. And because of the pandemic, remote work and online collaboration nowadays are more common and accepted. And this is no exception to software development. In the meantime, in the past few decades, eye tracking technology has significantly advanced. On the one hand, dedicated eye trackers become more affordable and accessible. On the other hand, even embedded webcams in laptops can perform eye tracking to a satisfactory degree. So combining all these factors together, we see a greater potential eye tracking can add value to empirical software engineering in terms of gathering rich data in a non-intrusive way and perform Gates analysis of developers, as well as the promise of Gates assistant developer tools. Naturally, this leads to our research question: how is eye tracking used in software engineering research? In particularly, in this paper, we look at it from a perspective of experimental setup. To answer the research question, we have conducted a systematic mapping study. Below is our search string. And this diagram shows you an overview of our filtering process. In the end, we included 71 primary studies in our final set. So what we have found, first, approximately 93 of the studies used participants, used students as participants. Some of them used only students, and some of them used a mix of students and practitioners. Second, approximately 85% of the studies were conducted in the laboratory setting. So you can mainly look at the green and the yellow bars. So based on these results, we have identified two clear gaps. First is a clear lack of Gates behavior of practitioners. Two, there's a lack of Gates behavior in realistic setups. So in the end, we discussed how can we bring eye tracking studies closer to practitioners. Overall, we want to bring more realism to eye tracking studies. This manifests in three aspects. First, of course, we want to find a path to have access to practitioners. Second, material-wise, we want the code to be more realistic in terms of its scale and complexity. And we want the task to have more realistic incentives because the Gates behavior will be very different, and the activities they can do be more realistic in terms of the editing of multiple languages simultaneously and switching of their code within the editor. We also make recommendations. More eye tracking studies have a stronger link with machine learning and using participatory design methods. Thank you for your attention.
We have time for one quick question. So I have a quick question. So you have different suggestions. Which one do you think is the most important?
I think it's the first one to actually have studies with practitioners.
A little bit more explanation, probably.
Because we have established these studies, although it's still a little bit controversial, the Gates behavior or experienced programs are significantly different from novices' Gates behavior, such as students. like experienced programs, they read code in a non-linear manner, whereas students read them in like literally line by line and in a very linear order.
Thank you very much.
Thank you.
Thanks. So thanks again for attending this session. And now we have finished all the talks, and I hope you enjoy the coffee break.